And welcome back, everyone. Mr. Armke back with you for A+ 10th edition Guide to Technical Support. We're getting into Chapter 8 today, talking about network infrastructure and troubleshooting. So our objectives are to explain TCP/IP and some standards that Windows uses for networking. We're going to ID, compare, and contrast hardware for building local networks, set up and troubleshoot wiring in a small network, often what we refer to as a SOHO, and troubleshoot network connectivity problems caused by three primary culprits: the firmware, operating system, and applications. Now, when two computers communicate at a local level on the internet, communication happens at four levels: the hardware, the OS, the application for each computer, and the network infrastructure itself. So that's all the routers, switches, cables, etc. So here we have a graphical example of what it looks like whenever we try and process a request. We have a web browser requesting the website cengage.com/index.html. It then is able to submit that request from the web browser through the internet to a web server according to the domain name. There's some DNS routing going on, but we're not going to get too deep in that just yet. The web server is going to recognize the request for the index.html page and return it to the client through the internet, basically reversing the chain that was just completed. And this is usually done through port 80 for HTTP traffic. Now, when two devices communicate, they have to use the same protocols. Protocols are just rules for communication. We can talk about it in terms of language, syntax, grammar, but it's just rules for communication. Almost all current networks use a group or suite of protocols known as TCP/IP. This stands for Transmission Control Protocol / Internet Protocol. TCP/IP deals with communication between two computers happening in a sequence of layers. TCP model is going to have 4 layers, whereas the OSI model would have 7. So the application goes ahead and passes a request to the OS, which passes the request to the network card, and then on to the network. In the TCP/IP model, protocols used by hardware function at the link layer, and protocols used by the OS are divided into 3 layers: internet, transport, and application. So here's the mapping, if you will, going between the two devices. So we see at the application layer where the browser is making the request. The transport and internet layers handle the operating system stuff, the internals, and then the link is the actual NIC, the Ethernet card. Now that's going to allow passing information across the physical medium, the cable, or the Wi-Fi going between these two devices. Now, as you go up or down these layers, you see that each of them has their own distinct type of address. At HTTP, we're dealing with the payload. The payload has to be segmented and broken up into what are called segments. Those segments are then repackaged a little bit and made into packets. Those packets are then given a header and trailer and made into frames. The frames are converted into bits, and that's what allows you to transmit across the cable. As it reaches the opposite side, the bits turn back into a frame, the frame gets stripped off and turned into a packet, packet turns back into a segment, and the segment turns into a piece of the payload. The payload is then reassembled into the completed file. So here we can see what each of our different layers do. Application layer deals with app-to-app communication, so things like HTTP, FTP, Telnet. This requires that a connection has already been made at the previous layer. Layer 3, instead of dealing with app-to-app, is now talking about host-to-host, and this is managed by the OS primarily with TCP and UDP. Now, TCP is connection-oriented, whereas UDP is connection-less. The internet layer deals with host-to-host on local network or network-to-network communication, and this is handled by the OS and network devices. So we can see here we move from port numbers, which identify programs, to IP addresses, which identify unique NICs. When we get down to the link layer, we're also dealing with unique NICs, but there's a big difference between a MAC address and an IP address. IP addresses can change. MAC addresses do not. So what I often tell students is the MAC address is kind of like the VIN number on your car. It's stamped on when it's built, and it stays with it through the entirety of its lifespan. An IP address, on the other hand, is much more like a license plate. You can hold on to it for a fairly long time, but when it switches out, it has to be swapped out for a different one, sometimes the same one if you're just renewing, and then it can go to a completely different state or different owner or what have you, and that has some significant amounts of variance that is possible. MAC addresses deal with device-to-device communication on the local network, what would be considered neighbors or link local. This is managed by the NICS firmware. The NICS firmware is embedded software that allows it to interpret different types of transmissions. Layer 1 is also called the network interface layer or network access layer. So here we can see the ipconfig/all command showing our physical address, aka MAC address, our link local IPv6, and our preferred IPv4 address, including the subnet mask. Now with this, we can see whether or not DHCP is attached. We can see DHCP server is listed. If there is a manual assignment, obviously that will show up a little bit differently. Now here we have a graphic showing that a router is going to allow or disallow transmission of a packet into a given network. So here we see the packet claiming I'm going to 168.30.45.6. The router, using OSPF, you can see that little lettering on the back of the person's jacket. My IP address and subnet mask tell me the host is somewhere in my network. Please wait here until we find it. And they're going to go ahead and establish a path of transition. So inside of a LAN, communication is done by MACs because it's a lot faster. And then communication is done by IPs when we have to go over the internet because we need a higher level of differentiation between local and remote networks. Here we see port communication dealing with TCP delivering an HTTP data packet. This packet is delivered as 138.60.30.5:80. So the colon identifies the port number. The computer here, represented by what seems to be a giant cardboard box, has two people behind a kind of lemonade stand style box. One is an email server at port 25, and the other is a web server at port 80. So because :80 is at the end of this address, that identifies the port that is supposed to receive and process the traffic. Now, as I said a little bit earlier, the TCP/IP model and the OSI model are very closely related, but the comparison is a little bit difficult sometimes because of the merging of layers that are done between the 7 layers of the OSI and the 4 layers of the TCP model. So here we can see the way that that's laid out. We can see that application, session, and presentation in OSI are all separate layers, but they get merged for the purposes of TCP/IP. Transport stays the same, and because TCP/IP is the protocol of the internet, the network layer, being a bit more abstract and more general, becomes the far more specific internet layer. Lastly, down at the bottom in the darker green, we see that the data link and physical layers in OSI merge into the link layer in TCP/IP. And as was said before, there are several protocols that are layer specific. So things like the website, the FTP server, the mail server, the RDP for remote desktop, all of that stuff happens at layer 4 for the TCP/IP model, but 5, 6, and 7 in OSI. We see that TCP and UDP stay pretty much where they are. IP, iGroup, OSPF, BGP, and ICMP are still kept at layer 2, 3 if we're talking about OSI. And then the hardline stuff for Ethernet frames, wireless frames, or PPP over a phone line are at layer 1 or 1 and 2, depending on your model. Now, IP addresses, depending on their version, will either be 32 bits or 128 bits long. Internet Protocol version 4, or IPv4, uses a 32-bit address to identify a network connection. There is currently a shortage of these addresses because 32 bits, 2 to the 32nd power, gives us about 4.3 billion possibilities, unique addresses, if you will. Now, the population of the planet, last time I looked, was passing near 8 billion. It's a pretty substantial amount. So if we assume that every person on Earth only has one device, we would have ran out a long time ago. Now, IPv6 was created partly due to this shortage, and it uses a 128-bit address space. Now, when a lot of people think about doubling the length of something, they think that, well, the space must get twice as big. Or, in this case, it would be quadrupling, so it's 4 times the size. Oh, no, no, no. When we're talking about 2 to the power of, 2 to the 33rd power, just adding an extra bit, doubles the sequence. So now it becomes around 8.6, 8.7 billion. 34 bits would be something around 16 or 17 billion. So we double it each time. Going to 128 bits means that we have somewhere around 38 undecillion individual IP addresses in this range. This means that there are more IP addresses in the version 6 space than there are grains of sand on the beach on Earth. The Internet Assigned Numbers Authority, also known as IANA, is responsible for keeping track of assigned IP addresses. So here we see an IPv4 address drawn out in several different categories. We have the dotted decimal version, 72.56.105.12. Dotted decimal meaning that we have 4 groups, 8 bits long, called octets, and each of them are representable from 0 to 255. So we represent this in binary as the largest possible 8-bit number, 11111111, which is essentially saying 2 to the 7th power plus 2 to the 6th plus 2 to the 5th plus 2 to the 4th, and so on, until we get 255. A little shortcut. If you ever have all ones in a binary number, identify the next place to the left. So if we assume 0 is our starting position, an 8-bit binary word has a maximum value of 2 to the 7th for its furthest left position. If we go 2 to the 8th, the next one up, that's 256. This means that the maximum value of an 8-bit word based on the 9th bit in sequence next is going to be 1 less. We have the 256, which means that the previous 8 bits added together will be 255. This is because we do not have any gaps in our integer mathematics for binary counting. So some IP addresses must be reserved and should not be assigned to a device on a network. There are 5 primary classes that we talk about. A, B, and C can be used for large, medium, and individuals or small companies. And then we have Class D, which is used for multicasting, and Class E, which is used for experimental and government addresses. Now, here's a couple of IP addresses that you may see pretty frequently because they're used a lot of time for testing. 127.0.0.1. This indicates your own computer, and it's called the loopback address. Technically, anything in the 127/8 subnet should be available for loopback testing. So it's anything that starts with 127 should be blocked off. I've not tested anything other than 0.0.1, but as far as I know, it's supposed to work. 4 zeros indicates a currently unassigned IP address. So if you see all zeros for an address that you're working with, obviously DHCP has not kicked in, and the manual assignment is not working either. All ones would generate a 255.255.255.255 address. This is used for broadcast messages by background processes to communicate with all devices on a network at the same time without needing specific recipient information. So an example of this is when a device would use DHCP to send out a request to any host that might be running a DHCP server to get an IP address, DHCP solicitation, if you will. Now, because broadcasting causes a lot of network chatter or noise, we create what are called subnets. This is where we take a network and divide it into smaller logical pieces so that fewer devices have to receive and respond to broadcast messages. Imagine that you have 1,000 devices on the same network and you send a broadcast message to them. So that's 1,000 devices that will have to essentially receive and respond to this message. What if we divided that in half? So we had 500 on 2 subnets. We still have the same devices and they still have the ability to access the network, but now when we broadcast, only half the traffic is being affected. Now, we tend to think of subnets in most professional circumstances as being even smaller. A lot of times what we'll do is deal with a subnet that only has 254 individual possible hosts. So we're keeping it under 1/4 of 1,000. Now, the first part of an IP address is going to identify the network and the host. When we look at IPv4, for instance, those 32 bits are traditionally going to be broken up and identified by a subnet mask that gives us what's called a CIDR notation. So here, let's take a look at our example, 192.168.80.1 through 100. This is a range of IP addresses that's assigned to a local network. Now, in this case, we are assuming that the first 3 octets identify a network because we have what would be called a Class C private network address, 192.168 as a prefix. Now, in this, traditionally, we will say, okay, let's go ahead and assume that it's a 24-bit subnet mask, meaning that the first 3 octets are going to be the network ID, and the last will be the host. So each of these in this range will have 100 hosts. If we were to have 192.168.80, 192.168.81, we may have some different networks. The subnet mask is what's used to compare the network address to identify a host versus a network ID. So let's take that. Every subnet mask has 32 bits and is a string of ones followed by a string of zeros. If I have an IP address on my computer of 201.18.20.160 and a /16 mask, which is 16 ones in sequence or 2 octets, the first half at that point would be the network ID. If you see all ones in an octet, that means that that whole octet carries over to the network ID. So that means that our network ID here is going to be 201.18.0.0. The host ID is going to be 0.0.20.160. Now sometimes an IP address and subnet mask are written using the CIDR notation I referenced earlier. You can see the /16 after the address, which indicates that the first 16 bits identify the network. Excuse me. For the curious, CIDR stands for Classless Inter-Domain Routing. The reason we say classless is because class-based IDs are the ones that are on multiples of 8. So /8, /16, /24. So here we can see how the subnet mask acts as a filter to decide whether or not a destination IP address is on its own network or on a separate one. So we see that we have an IP address 11000000101010001000010000000001. When we compare the subnet mask to the destination IP address, we get the ID of the network and the ID of the host. If we do the same thing with our own IP address, we can then compare the two networks to see whether or not they belong to the same or different networks. So the comparison here would allow us to say, is this our network or does this need to be sent to our default gateway to be routed somewhere else? Public, private, and automatic IP addresses. So public IP addresses are available to the internet. They're usually what's called public facing. Private IP addresses are used internally. IEEE recommends using the following IP addresses for private networks. 10.000 through 10.000 max, that's class A. 172.16.00 through 172.31.255.255. So one just below 172.32.0.0. 192.168.00 through 192.168.255.255. Now, computers that are unable to lease an IP address from this server type will generate their own APIPA address, automatic private IP, in the address range 169.254.xy, meaning that there's going to be something in those last two octets, but if it starts with 169.254, you know that it is an APIPA address. This means that it's going to have an address so that it can be identified on the network, but has not been assigned an address correctly by a DHCP server. So that means it'll have its own address, but it may not have, for example, a public private gate or a default gateway to be able to send traffic out to the internet. NAT, or network address translation, is a technique designed to conserve the number of IP addresses needed by a network publicly. So this means that we can take one public IP address and convert it into, let's say, a couple hundred private IP addresses. The router then is responsible for substituting the public IP address of the router for the private IP address of a computer that needs to communicate. Here we can see the NAT transition on the router moving from the 6932.208.75 address into a 192.168.40 address internally. IPv6 is a little bit different, as you might imagine. 4 times the length, 4 times the complexity, very much so. So in order to write 128 bits more comfortably, we tend to write them into what are called hextets, 8 blocks of hexadecimal numbers separated by colons. Now each hextet, each 4 hex characters, is going to be representative of, 16 bits of information, as each hex character is required to be represented by 4 bits, 4 of them together. 4 times 4 is 16. We can also perform what's called compression based on 2 rules. If we have a leading 0, meaning that, in the second block there we have all zeros, and in the third block we have a 0 in front of the B, there is no difference in their magnitude if we remove all the extra zeros from the front. Now, certain businesses, certain companies, certain organizations, Cengage included by the structure of this, do not like writing a compressed 0 block in this way. I have written it this way in the second line of the example. So 2001, 4 zeros, B80, 4 zeros, 4 zeros, D3, 9C5A, double C. In my mind, could be written even shorter as 2001, colon 0, colon B80, colon 0, colon 0, colon D3, colon 9C5A, colon CC. We can also use an extra elimination method called the double colon. If we were to take any blocks of all zeros and represent them with the double colon, we can only do it once. So you can see here that we could either take the first 0 block, which is block 2, or we could take the second 0 block, which is block 4 and 5, and eliminate those. I generally like eliminating ones that are a little bit larger, so that way we're optimizing the use of the double colon, but legally you could do it in either sequence. Just make sure, because using double colons more than once would create ambiguity, meaning that we don't know how many blocks are being represented by the double colons if there's more than one, we have to make sure that we only employ it once. Now in IPv6, we often use some terminology to identify different devices. A link is a local area network or wide area network that is bound in by routers. A node is any device that connects to a network, either logically or physically. The interface ID is the last 4 bits or blocks of an IP address. The neighbor identifier is given to those who are 2 or more nodes on the same local network. So neighbors physically could very well be neighbors logically, but that is not necessarily a guarantee. There are also some types of IPv6 addresses that you may or may not be aware of. Multicast, which we talked about a little bit ago, are packets that are delivered to all nodes in a targeted group. Those are the ones that in IPv4 would use the class D addresses. An Anycast address is going to be used by a router to identify multiple destinations and packets are delivered to the closest one. And then a unicast address where packets are delivered to a single node on the network. There are 3 different types of unicast addresses that we use. Link local unicast, which can be used for communicating within the same link. These are going to begin with FE80, and they're going to use a /64 subnet mask, meaning that the first half of the IP address for IPv6 is going to be the network ID. A unique local address, or ULA, is a private address used by network administrators when subnetting a network. And then the global unicast address can actually be routed on the internet. First 48 bits here being what's called the GRP, or global routing prefix, which is assigned by your ISP. So here we can see some different IPv6 addresses beyond what I just described. Multicast starts with FF00, link local starts with FE80, unique local starts with FC00, global address is 2000 with a /3 subnet, so it's only going to be the first 3 bits that is defined by the subnet. Unassigned, which is very much like IPv4, all zeros, and then the loopback, which is 0:1, or just :1, which is 127 zeros in sequence followed by a 1. In a command prompt window, in order to check out some settings, we can use the ipconfig command to show some different addresses that are assigned to our different physical and logical interfaces. Now, when a computer using IPv6 makes a network connection, it's going to go ahead and generate its own IPv6 address by using the FE80/64 prefix, and then use its MAC address to generate an interface ID for the last 64 bits. It's then going to perform a duplicate address detection process to make sure its IP address is unique on the network. It will check with a DHCPv6 server to see if it's present on the network to provide configuration information, and if such a server responds, then the computer will use it. Here we can see that information being applied in the IPv6 interface towards the bottom. We can see that we have a both link local and standard IPv6 address in the tunnel adapter from Teredo. Now, character-based names allow us to identify computers and networks much more uniquely. Human beings are built on narratives, so we look for names, we look for stories, right? Character-based names are often used to substitute for IP addresses, and that's how we get things like host names or computer names. We may also have a work group, that is a name for a group of peer-to-peer devices that are sharing resources. A domain name is how we identify a network. A domain name that is fully qualified will also identify the computer and network to which it belongs. This is quite closely related to like CNN.com or Craigslist.org. These are fully qualified domain names that identify a source domain with a top-level domain, a TLD, at the end. DNS services and protocols help handle that name resolution process, being able to move from IP to a recognizable character-based name. When Windows is trying to resolve a computer name to an IP address, it'll check in its DNS cache, and if this is not found, Windows will turn to the DNS server to find IP addresses. This is called the DNS client. Now, TCP deals with guaranteeing delivery. Transmission Control Protocol, it's an oriented protocol in terms of connection, meaning that it has to establish a three-way handshake before it begins transmitting. When a TCP message reaches its destination, an acknowledgement is sent back, and if the source does not receive the acknowledgement, it will either resend or pass an error message back. So this allows you to determine whether or not your transmissions are working correctly. UDP is more about speed than integrity. They are going to say, okay, well, let's just go ahead and start sending, and if you get it, great. If not, not a big deal. It's a connectionless or best effort protocol, and it's used best where broadcasting means guaranteed delivery is not as important as fast transmission. So things like video conferencing, voice over IP, these are areas where we just want to make sure that we're continually transmitting. We're sending fresh information. So for live broadcasts, things like that would probably be UDP. UDP is also better used to monitor network traffic. Here we can see IP and TCP working together to make a delivery. They're dropping off the HTTP data with the transport service, and the acknowledgement is being sent back. Some other protocols being used by applications in the TCP/IP stack. HTTP, Hypertext Transfer Protocol, both its standard and secure versions will allow us to communicate with web browsers and servers. SMTP is going to send email messages. POP and IMAP is used for delivery. RDP is used by Windows Remote Desktop and Remote Assistance, and Telnet is used to remotely control a computer, no native encryption included. You may also see on certain cases SSH, or Secure Socket Host. That is able to basically do the same thing as Telnet, but it's going to be in a secure encrypted environment. FTP, File Transfer Protocol, transfer files between two computers. Secure FTP, or SFTP, employs SSH encryption and SSL encryption. SMB, Server Message Block, this is used by Windows to share files and printers. Apple Filing Protocol, AFP, this is an early Mac OS protocol that was used to do file access. LDAP, which is Lightweight Directory Access, this is used by clients when an application needs to query a database. And SNMP, Simple Network Management Protocol, this is a traffic monitor. Now, when we talk about local network infrastructure, we're talking about things like your actual desktops, laptops, tablets, phones, hubs, switches, bridges, other network devices, and then the connection media that goes in between these devices. Most wired networks use what's called a star bus topology, where nodes are connected to one or more centralized hub or switch. And you will sometimes see what's called an extended star or hybrid topology, where you have a star within a star within a star. A hub is an outdated piece of technology that traditionally just acts as a pass-through device. It will essentially reproduce and regurgitate any data that is sent to it on all ports except for the one that it arrived on. Now, a switch is very much like a hub, but it keeps track of all the MAC addresses for devices that are connected to it. When a frame is received, the switch goes ahead and searches the MAC address table for the destination MAC and sends the frame only to the device with that address. If the destination MAC is not in the table, the switch will send the frame out of all ports except the one for receipt. Very similar to what we talked about with the regenerative properties of the hub. Now, when we talk about a switch, we usually refer to one of two versions, managed or unmanaged. Unmanaged means that there's no setup or config that's been set up to make the switch behave any particular way. It's plug and play. A managed switch is going to involve firmware that can be configured to monitor and manage network traffic, creating what are called VLANs or virtual LANs, virtual subnets that can help reduce our traffic, as well as making sure that we are able to effectively filter traffic should we need to. So why would we want to add a switch? Well, to add network connections, to be able to improve our ability to host multiple devices simultaneously. Regenerating a network signal to allow it to pass over a greater distance without losing it to attenuation. And then managing network traffic, being able to reduce congestion, things of that nature. So here we can see a hub over here on the left, simple pass-through, whereas the switch is actually able to make decisions regarding traffic history, being able to send things directly to a destination node based on its MAC. Here we have a managed switch that is able to handle transition of information between two VLANs or virtual LANs. So let's say that the VLAN number 1 belongs to the sales department of a company, and VLAN 2 is going to deal with the management side. This allows them to keep their traffic separate so that we can make sure that they're not overstepping on one another and that there is not any potential for misdelivery of messages. A wireless access point is very similar to a hub or a switch or a router in that it allows connectivity to the network, but instead of using a hardline copper cable, it's going to use radio frequency. They may double as a router. They can also be a bridge. A bridge essentially is like a switch, except for it's just going between two segments of a network. So if you wanted to join two switches together from a smaller branch line, if you will, you could do so using a bridge. So here we see that bridges make decisions regarding network traffic. If we're seeing traffic coming from, for example, house A, and it's looking for house B, the bridge essentially is going to say, hey, what you're looking for is not on this side, so you're going to stay on your local network. Now, there are other things that would help a packet to identify a link local neighbor, if you will, but the bridge does also have that secondary layer of filtering. Network servers. Some servers are standalone, but often multiple network services are provided by a single server computer. Servers may also be embedded in a device. On large networks, network services are often provided by multiple servers so that if one goes down, others can fill in the gap. This is called redundancy. Essentially, we are making sure that if a particular service is unavailable on one device, that we have a backup, something I'm sure you've seen before. Client-server resources used on networks and the internet would be things like web servers, mail servers, file servers, print, DHCP, DNS, proxy, authentication servers like Kerberos or with Radius or TACACS, syslog servers. Unified Threat Management, also called UTM. These types of appliances are often called next-generation firewalls. These are going to combine basic firewall functions that just basically separate network traffic and adds in antivirus and anti-malware as well as other basic functions. An NGFW device can offer comprehensive unified threat management services, meaning that it's going to include some kind of basis of security, network appliance, or internet appliance, which stands between the internet and a private network. It is acting as a barrier. Now, a UTM can include a couple of different types of services: firewall, AV, and malware, as I said, identity-based ACLs, or access control lists, intrusion detection and prevention systems, endpoint management servers, and even a VPN to allow you to remotely access secure resources. So here we can see a UTM appliance connecting a remote item, a laptop in this case, to a private network as if it were physically present. Now, Ethernet, we're talking about cabling, is pretty far-reaching. It's been around since the 70s. 10 megabit per second Ethernet was invented by Xerox. They eventually upped it to where it was able to move at 10 times the speed, to where we got 100 megabit per second Ethernet, also known as fast Ethernet. That's the traditional stuff that you're mostly going to work with. If you get into gigabit and things like that, then obviously you'll start working with 10 base 1000, which is our gigabit Ethernet cabling. Uses the same physical cable and connectors, it just uses a different signaling algorithm. Fast Ethernet only uses 4 of the 8 leads internal to an RJ45 cable, whereas 1000 megabit internet uses all 8 in most cases. 10 gigabit Ethernet traditionally uses fiber optic cable, and this is a good choice for network backbones where networks essentially connect to ISPs, larger infrastructure. Twisted pair cable is the most popular cabling for local networks. This is pairs of thin wires twisted together to reduce crosstalk. Essentially, if we have two wires that are running side by side, the likelihood that they're going to interfere with one another becomes very high. So what we do is we twist it on a 45-degree angle to where they're essentially crossing over each other at a 90-degree angle. The cable on the left tilts in 45 degrees to the right. The cable on the right tilts in 45 degrees to the left. There's minimal amount of loss of length. You're not changing physical direction as dramatically as you would be otherwise, and they are able to adjust that cancellation effect. We're also able to do two different varieties of cable, where we could have an unshielded twisted pair or a shielded twisted pair. Unshielded is the most common and least expensive. Shielded twisted pair will then use a covering or shield, usually made out of foil, that wraps around each pair of wires to protect it from electromagnetic interference, or EMI. Sometimes they'll also have like a little core separator in the middle to help keep them separated, and a foil jacket that goes over the cable as a whole. So it's a lot more expensive to produce. It's a lot more time consuming to produce. So of course it's going to have an exorbitantly higher cost relative to UTP. So here we can see some statistics about Cat 5, Cat 5e, Cat 6. The E stands for enhanced. The idea is that you're going to have a little bit more heavy-duty resilience in the actual cabling itself. So Cat 5 standard usually only uses 2 wire pairs. Cat 5e will use 4. And then Cat 6 is also going to use 4 wire pairs, and traditionally is going to be supportive of gig and 10 gig Ethernet. Now, the separator that I talked to you about a little bit earlier for Cat 6 is usually going to be shaped like a plus sign or a T, and it helps to keep the wires apart from one another. So here we can see the Cat 6 on the far right, Cat 5 and Cat 5e in these two on the left that have their heads removed. You can see the wires are slightly thicker on standard PVC, slightly thinner on plenum grade. Plenum grade is used for spaces in between the ceiling of one room and the floor of the one above it, because it does not release toxic smoke when it burns. PVC, polyvinyl chloride, definitely will. Fiber optic cables transmit signals as pulses of light over glass or plastic strands inside of protective tubing. Comes in 2 different modes, single and multi. Single mode uses a single path for light, and multi-mode uses multiple paths for light. See, we can be creative. Both single mode and multi-mode can be constructed as loose or tight buffered cables. Loose tube cables for outdoor use have a little bit more flex. Tight buffered tends to be more for indoor use, where it's not going to be kept under thermal or physical or mechanical stress. Power line networking, or EOP, uses the power lines in a building to transmit data. It's pretty simple to set up. If you share an electrical signal or a phase with another building, data could theoretically leak, but this is unlikely. Most places I've installed EOP are in residential buildings. Power line adapters offer a bit of encryption that's offered by pairing the adapters to one another. This is a 128-bit AES signal. In order to use power line networking, you need at least 2 power line adapters. Now, there's also what they call PoE. When you get into EOP, you have to remember that they need to be plugged directly into a wall outlet, not into a power strip. They don't work in a power strip. The adapters themselves might be kind of large because they do have some circuitry in there that allows them to signal accurately over those electrical frequencies. They may cover both outlets on a single wall plate, so just make sure that you have enough space in your designated area. And the distance that it has to travel is going to degrade the quality. So if you're dealing with like a 3 or 4 story building, you may want to try and figure out a slightly different solution, or you can look for ones that are specifically designed for longer distances. There are some high-end industrial ones that are specifically built for longer distances. Now, PoE is a feature offered on some high-end network adapters to allow power to be transmitted over Ethernet cable. This is so you can place a device in a position where you don't have an electrical outlet. If your switch doesn't offer PoE, you can actually add it using what's called a PoE injector. On the other end, the injector has to be able to receive and filter the signal and pass it through what's called a splitter. So if you have to add the signal, you have to have either a PoE device on the opposite end that will automatically interpret it, or you have to have a splitter that will separate it into power and data signals that can then be interpreted by a normal device, non-PoE. So here we can see the splitter coming off of the other side. We can see one that is for a separated power and data device. You can see those 2 ends coming off of the little box there. Now, setting up and troubleshooting wiring. If your network's not strictly wireless, you'll probably also need some cabling and switches to create a wired network. So this is going to cover that basic setup and troubleshooting. Always plan your design first. Planning is always critical. So try and place your hotspot or access point near the center of the area to maximize its range. if you're concerned about covering a particularly large area, you may want to take a look at what coverage area you can expect from your particular Wi-Fi standard. Wi-Fi standards vary pretty broadly, especially in the modern era, so make sure that your network covers the space that you need. If you have to, you can always get a secondary hotspot and connect it with a fairly long cable. The length of cabling at maximum between two infrastructure devices that will regenerate the signal should be no more than 100 meters or roughly 330 feet. Which, if you think about it, is a pretty long amount of cable to run, even if you're having to go around doors, things like that. So again, positioning has to be strategic. Some network cables may be wired inside of walls with wall jacks that use RJ45 ports. Be aware that those cables will need to converge somewhere that is easy to access for an administrator, but difficult to access for conventional employees or visitors. We usually call this a data closet or a patch closet. For best performance, follow the rule about length. So for twisted pair, 100 meters. Try and use Cat5e or better, simply because standard Cat5 really doesn't get sold anymore. For switches rated at the same speed as your router or network adapters, you are going to get the best performance. If you have equipment that is not balanced in this way, you'll get what's called bottlenecking. So let's say that you have a really awesome switch and a really awesome router. If your cabling is junk, you're not going to be able to get consistent signals. If you have an awesome router but you have a poor switch, not so good. If you have an awesome switch and an awesome router but a poor NIC, like the network adapter on your computer, only runs at 10 base 10 or something similar, then you're definitely going to have a difficult time getting consistent high delivery internet traffic. So again, there's a lot of pieces that come together to deal with your infrastructure. So you have to look at the NIC on the device. You have to look at the cabling or other medium that it's using. If it's using Wi-Fi, obviously that's radio frequency. You have to look at the AP if you have one. You have to look at your switch. You have to look at your router and anything in between. This is definitely not an easy project if you're not doing the planning. So plan. So here we have the plan for a physical configuration of a small network. We see that we've got some desks here. We've got some wall jacks that we're going to set up. We've got a placement for our router and our modem, otherwise known as our primary gateway. We have a network access printer, and we can see that there are some cables that are probably falling through the walls, if not over the ceiling. So this is a very rough sketch, but at least it gives an idea of some physical placement. So this is what we would call a physical topology for the layout. A logical topology would just be how they're related to each other. So that cable modem would obviously be at the top, the router would be just below it, and then secondary switches beneath that with end devices below those. What are some tools that we may use as technicians? Well, that list could be very long indeed, but let's talk about some of the big ones. A loopback plug. This tests to see whether or not a port on a switch matches up with a wall jack, if a port works, and what speed it may be running at. Cable testers can do the same thing as a loopback plug, but they're essentially just doing it to a cable. Network multimeter. This will allow you to test cables, ports, NICs, etc. Tests all kinds of different information about that particular media or interface. So here we see a cable tester, just a basic one with the little BNC caps on the end, allowing you to connect them together. We may also use things like a Wi-Fi analyzer, software that can help us define networks, determine signal strength, optimize them, as well as identifying Wi-Fi security threats. A toner probe. This is a two-part kit that can be used to find cables in walls. Cable stripper, crimper. These are in order to cut your own network cable. Punch down tool, also called an impact tool, allows you to essentially slot individual wires into what's called a keystone jack. It almost looks like cartoon joke teeth in that there are 4 little slots on each side separating each of these big rectangular protrusions from this little package. And once you punch these cables in the correct order, you're going to use either 568A or B standards, you can then face this jack into a strike plate for the wall and be able to access it just like you would a telephone jack or a power plug or a cable. So here we have a Wi-Fi analyzer app, and we can see the strength thereof. We can see what channels they're occupying, etc. Here we can see a toner probe kit by Fluke, and we can see where we can test the connectivity. There's a crimper. I have one from Paladin that's very similar to this. It's almost exactly the same. It's just orange instead of blue. Punch down tools. These are very simple. Those tips can sometimes, you can see the little ring around the collar there, that can be slid down and lifted out. You can get a type of a pressure-based tool that is square on both ends instead of with a cutter tip, in order to just punch down the cables without possibly damaging them. It could be a little bit easier for novices to go ahead and punch the stuff into place without damaging the cable and trimming it off, and then going back with a razor or similar later on. So let's talk about how these cables are hooked up. As I mentioned, there are different standards for wiring when we were talking about the Keystone Jack. Straight through cables are used to connect computers to switches or other devices. This is often called a patch. That's the most common cable type that I use. Crossover cables are used to connect two like devices, such as a hub to a hub or a PC to a PC, without infrastructure between. This is where we're going to essentially flip the transmit and receive lines on one of the devices. So transmit on one end becomes receive on the other, and vice versa. An RJ45 connector has 8 pins, and as I said, 10 and 100 base T Ethernet uses 4 of those pins. Gigabit uses all 8. Twisted pair cabling are color-coded in 4 pairs, solid and striped for each. So you have brown, green, orange, and blue. The standards are 568A or B, and they look like this. So 568A, meaning that if we were looking at this thing from the top down, as it were, we can see the cables lined up as green is 1 and 2, orange is 3 and 6, blue is 4 and 5, and brown is 7 and 8. Now for 568B, this is largely the same. All we're going to do is transpose, as I said, is the transmit and receive. So orange and green are going to switch places. So the orange and white switches with green and white, and the orange solid switches with green solid. So 2 switches with 6, and 1 switches with 3. Very easy to accidentally mess up. So you always want to make sure you got some practice in. If you've got color blindness or anything like that, there's a couple of different methods that we can use regarding that. I personally have red-green color blindness. It's not very intense, but it does sometimes mess me up, especially with the more aesthetically creative cables, making sure that I've got the correct layouts. So here we can see the pinout for each one. Transmit and receive, as I said, for standard Cat 5E and 6 is going to be on our green and orange lines, whereas blue and brown are going to be gigabit only. So here we can see the crossover, how they lay out, connecting from one to another. And here's a handy little flowchart to troubleshoot networking problems related to hardware. We want to start basic. Try ping, try more than one device. If it's just you versus just the network, that's a big difference. What can we access? Have we tried a loopback plug? Have we tried a cable tester? Etc. We want to start from least invasive and work our way up. Now, if we have issues with intermittent connectivity, that could be a damaged cable, it could be a NIC issue, it could be a problem with DHCP. We want to make sure basically that we just go through the list and make sure that we're writing stuff down as we're working. Check your hardware, move into network settings, check your indicator lights, make sure your cables are nice and snug. Something that happens to a lot of people is that the little tab that you press down to release a Cat 5e or 6 cable from a NIC essentially will snap off. It's very thin plastic. Sometimes it gets kind of brittle, especially if your computer runs kind of hot. That plastic gets kind of thermally sensitive. And then when you push the cable back in, it doesn't have anything to click into, so it just slides back out. So you always want to make sure that if for any reason that gets broken, you have a different way of securing the cable, or you replace the head. For wireless networking, always make sure that your switch on your laptop for wireless is turned on. You may have to go into a couple of different places to figure out how to do that. Different laptops may or may not have a function key to allow this. After you've checked your hardware, in Windows we can use ipconfig release and renew in order to try and flush the internal cache for the network device. In Network and Sharing Center, we can actually run the basic Windows troubleshooter. That surprisingly has saved me a couple of times, because as a technician, when you're in it for a while, you start accidentally overlooking things that would normally jump right out at you. So never stop learning, never assume that you know it all, that sort of deal. Go to your Network and Sharing Center and change your adapter settings. Right-click the connection and hit Disable, and then after that turn on Enable again. In Windows 10, I think 8.1 as well, in the taskbar above the network adapters, if you click on it, there'll be a little context-based line that says Enable and Disable that'll pop up. If there's still no resolve for this, go ahead and check your drivers. Sometimes that can be problematic. I have had issues with wireless NICs in the past, especially with Dell, unfortunately, that the update actually caused more problems than it solved. And then when I removed it, it was perfectly fine. And then a couple of days later, I reinstalled the same driver update and it works perfectly fine. But for some reason, I don't know why, it's just my experience that with a particular set of Dell laptops I've owned over the last 5-10 years or so, certain Wi-Fi updates I have to be very, very guarded about rolling back if they don't work right away. And also always pay attention whenever it tells you to reboot after installing a driver or doing some kind of major change. Go ahead and run the reboot. There are certain things that don't get cleared out of the cache of the system if you don't reboot. Of course, check your antivirus software, check your firewall. That can be a big issue. Sometimes traffic can get blocked inadvertently. If you have local connectivity but not internet access, try recycling your connection to your ISP. What I like to do is turn everything off. I turn off my PC, I turn off my router, I turn off my modem. Once that's turned off, I will turn off the modem. I'll turn on the modem first. I'll give that a little bit to connect. Then I'll turn on my router. Then I'll turn on my device. If you have a cable modem and you have other services from your cable provider, make sure your TV works, or make sure that your home phone, if it's done through VoIP or things like that, will also work. Basically, what we're trying to do is make sure that we're not missing something obvious when one service from the same connection works and the others don't. To eliminate the router as a problem, we can go ahead and do what's called a direct pin. We can go ahead and connect the computer directly to the modem. This is why I don't like router, modem, wireless router combos, because it makes it harder to troubleshoot. There's a lot more internal stuff you have to start dealing with if you can't pinpoint who's got what problem. If you can access the internet directly from the modem but not from the router, then you've proven the router is the problem. There could be any number of things in the router that are issues. You could have port forwarding configured incorrectly. You could have certain MAC addresses filtered, that sort of thing. If you have local connectivity, you can also check and see if your DNS server is giving you trouble. I like to use DNS server 8.8.8.8. That's a public DNS from Google. There's also one, there's a OpenDNS. There's a couple of different ones floating around on the web. There's some great reviews, but there's also, people who might be trying to harvest your traffic, so always be aware of that. If you're having trouble reaching a particular website, you can try the traceRT command, traceroute. What that's going to do is essentially it's going to run a ping, but every time it gets to a new device, it's going to increment the TTL and send back a packet, excuse me, so that you can identify which device the route stops with, essentially. Check your router firewall as well as your Windows firewall, and then you can contact your ISP. Strangely enough, what I have run into is if I troubleshoot it myself and then call Time Warner, it seems to be pretty fast that they can fix the problem, because then all they do is, if everything's good on my side, all they do is send the cycle message from their end, and it seems to clear it up. Now, it can be very frustrating because you go through all of these steps, even if you've documented, and you tell them, okay, I've done this, I've done this, I've done this, I've done this. They have a script in front of them they have to follow. So it can be frustrating, but just go along with it. Do what they ask, so that way you can go ahead and make sure that it is not on your end. Because what you don't want them to do is have to send out a technician for something that could have been done with just a phone call. Now here we can see somebody using the 8888 that I recommended. 8844 is another one of Google's. If you're having issues with verifying your local computer's communication system, just ping yourself. You can ping your own IP address, or you can use the loopback address 127.0.0.1. If you have a static IP, what I will often do is temporarily disable it and try and use DHCP. If that works normally, then that says to me that I need to check my settings for my static IP. What I will often do is make sure that the static IP is established on my router first if I have to. I have used routers in the past that don't allow you to assign static IPs directly on it. It has to be done on the device. I'm not really fond of that. But if you do it on your router and you do it on your device, you will have to restart both of them so that they can see each other. ipconfig/all will allow you to verify your IP. Try pinging other computers on the network. I like pinging my TV because it's hardwired, so it tends to not change around a lot. Netstat-B will actually make sure that the access program for the network is really running. And verify your firewall, of course, and then you can always test using a network drive map. Now, this is a little bit more advanced than I would want to use for introductory students, but it does work. Netuse z:// whatever your computer's name is, and then a folder. You can obviously substitute different letters if you want. What this is traditionally used for is to make your device's internal drive, or internal folder rather, available as a individualized network share. So you can set it up to have permissions, and certain username and passwords are allowed, things like that. I do it with empty folders if I'm testing. That is what I recommend. And then in order to remove a mapped drive later, you would just go to netuse z and then space/delete, because Z is already established. We just have to go ahead and remove it. The net use and the net command prompt, pretty handy stuff. Now, if your network seems like it's slow, let's go ahead and start at the hardware level and work our way up. Unofficially, the user level, layer 0. Link layer, this is going to essentially be checking cables, checking lights. Internet layer, that's when you test ping. Transport layer, go ahead and check your firewall. And then application layer, what I often find is that there's something wrong with the firewall. That's really the most common if I get up that far. But the application layer, on occasion, you'll have to check compatibility, things like that. That's when you really start calling the real help desk team, because those kinds of fixes are usually a bit beyond conventional users at first. But again, you can always Google stuff. You can go on, iFixit or things like that and try and figure out. I'm running into this error, especially if you have an error code. By goodness sakes, if you have an error code, just Google it. If you can't find a Wi-Fi network, the SSID might actually be hidden, so you may have to type it in manually. If you know the name and the security key, you can actually manually connect and type everything in. Make sure you don't fat finger it like I do, or my wife calls it sausage fingering, to where my hands are a little bit larger, so I accidentally will sometimes catch the edge of a key and not realize it, especially hitting the enter key if I accidentally hit the / key right above it as I'm hitting enter. Because I try and type quickly, but sometimes I'm not always the most accurate, especially on low profile keyboards. I'm very spoiled with my mechanical. But once that's set up, you should be connected. If that doesn't work, then you may want to try essentially deleting the network name and then trying to sign in again. Do you have another device that you can try testing? That sort of deal. And that is our Chapter 8. So if you have any questions or concerns, as always, you can always contact me via my Google Voice number, 239-7814, or you can send me an email at jearmke063@cfcc.edu. It has been my pleasure to try and be at least slightly entertaining over this material, and I hope to see you again soon, and I will talk to you next class.